Okay, so, the last lecture was all about being able to categorize your electron pushing arrows into those categories of being nucleophilic attack, loss of a leaving group, resonance, what was the other one? Proton transfer, and then rearrangements. And rearrangements were one I told you I was specifically leading to this lecture because there's something that are unique to carbocations. And carbocations are such an important part of organic chemistry. So I wanted to give it its own little topic, right? So first of all, we've talked about carbocations before. These are carbons that have 3 bonds and no lone pairs, which means that they have an empty p orbital. They only have 6 electrons in their octet. That empty p orbital makes them really good electrophiles. So we're going to see carbocations playing the role of an electrophile in a ton of different reactions throughout the semester. Okay. So let's talk about properties of carbocations. So we actually talked before, sort of mentioned before about if we want to like focus on this scale down at the bottom here, not all carbocations are created equally. Methyl carbocations are relatively unstable, as well as primary carbocations. But secondary and especially tertiary carbocations are stable. And an allylic carbocation, right? So remember this is the allylic position relative to this double bond. Allylic carbocations are also very stable. They're about equally as stable as a tertiary carbocation. So what is it that makes adding methyl groups, or not methyl groups, but adding, carbon-carbon bonds, what is it that stabilizes that carbocation? It's actually that very weird phenomenon we talked about before of hyperconjugation, right? So we talked about hyperconjugation as why the staggered conformation in our Newman projections had quite a bit of stability. It's the same effect that's stabilizing a carbocation. The bonding orbital, this is like the hyperconjugation imaged here. This is the bonding orbital of a carbon-hydrogen bond is overlapping with the empty p orbital in a carbocation in such a way that stabilizes that p orbital. And the more of those carbon-hydrogen bonds that I have to hyperconjugate with my empty p orbital, the more stable it is. So that's why adding more, if this was a methyl or carbon and this was a carbon, it would increase the stability of that carbocation that much more. Hyperconjugation, rearing its ugly head. Okay, now 2 types of rearrangements occur with carbocations. The first is a hydride shift. So let's see if we can figure out what's going on here. Here we have a carbocation, and right next door is a secondary carbon. Well, there's going to be a hydride shift, meaning the hydrogen from one carbon is going to jump to the other, which is also means that the positive charge is going to switch places, right? So this hydrogen is taking its electrons that used to be in this carbon-hydrogen bond and now sharing it with this carbon. So that effectively has shifted the position of the hydrogen as well as changed the carbocation. So why? Why would a molecule do this? Well, notice how over here I have this nice stable tertiary carbocation, where over here it was secondary. So the reason why a molecule will rearrange is in order to produce the most stable carbocation. Okay. Another type of shift that you can have is a methyl shift, which is, kind of just like what it sounds. Now, instead of a hydrogen moving, it's going to be an actual methyl group. So notice here, we have the actual entire methyl group. So what would we expect our products to look like? So again, not only did the methyl group jump from one carbon to the other carbon. I guess if I can color code my carbons here, this was this one. But also that positive charge has also shifted. Okay, and again, the whole idea was we went from having a secondary carbocation to a tertiary carbocation, which is that much more stable. So these rearrangements can occur for carbocations in order to form the most stable one. A shift can only occur from the adjacent carbon. So it's not going to be one on the other end of the molecule that does any sort of shift. You're only going to be looking at your next door neighbors and asking, does a shift occur? Okay, so let's try to spot whether or not a shift will occur in a given situation. Okay, so again, only carbocations that we have to worry about. So given this carbocation, what am I going to do? I'm going to first look at its next door neighbors, because these are going to be the only two culprits here. Okay. Now I'm going to look at what's bound to those different groups. All right, so over here, there are two hydrogens, and over here on this other one, there's a hydrogen and a methyl group. Right? So one of the things is like, okay, which one of these is going to lead to a more stable carbocation? Currently, I have a secondary carbocation. If I moved it over here, this would still be a secondary carbocation. But if I could get it over here, then it would be a tertiary carbocation. That's more stable, right? So that's how we identify what's going to happen here. In this case, we will expect to see a hydride shift occur in order to generate that tertiary carbocation. So yeah, so we identify which groups is going to yield the most stable carbocation, and in this case, a hydride shift can achieve that. Now, why is it a hydride shift instead of a methyl shift? Well, so notice, I'll actually just draw it here. Notice that if I had done that, I had done a methyl shift instead of a hydride shift, there would still be a hydrogen here. And this methyl group would be up here. This is still secondary. Right? So a methyl shift wouldn't have created a more stable carbocation. So if there is a hydrogen, it's going to be a hydride shift. Okay, so that is not what happens. It is a hydride shift that occurs that generates that more stable carbocation. Okay, and the same thing we can kind of expect to occur for allylic carbocations, right? Remember that allylic carbocations are super duper stable. So here, again, I have my carbocation. I'm going to identify all its possible next door neighbors to see whether or not that positive charge would be happier here or on any of those. And indeed, this would be my most stable carbocation. Not only is it tertiary, but it's tertiary and allylic. It's like got all the good stuff going on, right? So here I can establish that there would indeed be a shift in order to put the positive charge on that side. Again, is it hydride or methyl? Let's look. What's being bound to this carbon? Well, I have my 3 explicit bonds, but also, I guess I'll put it up here just for clarity, also this hydrogen here. So it's going to be a hydride shift that occurs and leaves me with a positive charge in the allylic position. Right, so when you're trying to look out for, does this hydride shift occur, you're looking for, can I put it on a more higher order carbon, a tertiary carbocation, again being the most stable, or can I put it in the allylic position, because that will also have added stability, right? Stabilize through resonance. Okay?